I wanted to reiterate about this up here for those of you that came in a little bit later. This on the left is showing you 1%, 1 part per 100. And this is a block of, well, I don't know if it's 10 of those across. I think it's more. This is a block of 1 million little dots. And you can see right here, one of them has been highlighted. So this is demonstrating for you the scale of parts per million. All right, let's start with sig figs. I think one of the most important rules about sig figs that is challenging to communicate, challenging to get into problems even, is that the first operation determines your number of significant figures. You know, there was a question like this on the unit test where you did multiplication, division, addition, and subtraction. So how are you supposed to know when or how you limit? Do you limit by subtraction addition rules, which is the least number of decimal places? And do you do that right away, or do you carry them all out and then do it at the end? Or do you just do your last operation, the operation you do the most? The answer is whatever you do first is going to limit your number of significant figures. So as a review, subtraction and addition limits to the least number of decimal places. And we did some practice problems in class where the least number of decimal places was actually like the tens place or the hundreds place or the millions place, right? This doesn't have to actually be on the decimal or beyond the decimal place, but it can be above it as well. So we're limited to the least number of decimal places. So let's say you do a calculation, subtraction or addition, and you're limited to the least number of decimal places. Let's say that gives you 2 decimal places, 1 digit in front, so you're limited to 3 sig figs. Now you know that you've got 3 sig figs at the end of the answer. Not that you've got 2 decimal places at the end of the answer. Sometimes that would mean that you actually will end up getting a ton of significant figures. But you've limited it by decimal places. In that step, now you know the number of significant figures. If you're doing multiplication or division, limit by the least number of sig figs. Remember that every answer that has significant figures, that last significant figure is the uncertain digit. We can't be certain about it because there's always some variability to it. If it's 4 or lower, you round down. And if it's 6 or larger, you round up. And then we've got those weird instances with 5, right? If it's 5 exactly, round to the even number. And if it's 5 with zeros after it, round to the even number. But if it's 5 with anything after it, even if it's mostly zeros, then you round up. You guys are okay with this rule, by the way? Are you comfortable with 5 being a true tipping point and not actually being able to decide whether you should round up or down? So we just have to decide always round one direction, round to the even number. Anything that you guys want to add to that? Anything you still feel confused about? Gabriel.
Can you just do like 2 examples, like one with addition?
Yeah, for sure. We're going to do molarity conversions, and we're going to do photon calculations as well, but you want to maybe just see different ones. All right, let's say that I have a material that weighs 1.005 grams, and I'll add this to a material that weighs 12.5 grams. And then let's just get density here. So let's say that we divide this by some volume, 20.61 milliliters. What's my first operation? What'd you say, Kay? Oh, we don't have to. No, we don't have to convert the units at all. We got to do addition first. Because it's written on the top, really we could have put this just in one big parentheses to say, I'm going to add these two masses together and divide them by the volume. How could I do it otherwise, right? I'd have to divide each of those numbers separately and then add them together. So order of operations here is add these together, which means we're going to find that our significant figures is limited by the least number of decimal places here. When I add these together, I get 13.5005. No. 13.505 grams divided by 20.61 milliliters. I'm limited to how many decimal places on top? I'm limited to one decimal place, which is here. So how many sig figs should I get in my final answer? 3 sig figs. So why haven't I written it with just 3 sig figs? Sorry? I'm going to round at the end. If I were going to round it exactly where it is, what would I round that number to? 13.6? 13.51? 13.6? I'm going to write out a few options. Would I round this to 13.6? 13.51, 13.5, 13.50. Debate. If I were going to round now, what would I round it to?
I think you'd round to 13.6 because we need to round to 3 sig figs. And since the 5 at the very end is greater than 0, we need to round up to 13.6.
Okay. Not that it's greater than 0.
Or greater than 4,
But it's actually like this condition. It ends at a 5, it's even, so we would round, or we round a 5 to an even number. Is 5 controlling the rounding? Is this 5 at the end controlling the rounding of my uncertain digit? So then why do I want to round using the 5? What number am I using to round the 5? I'm using the number exactly after it. I'm using 0. Does 0 fall into equal than or less than 4, or equal than? Equal to or less than 4, or equal to or greater than 6? Where does 0 fall? It's less than 4. So I'm going to round down. So how come I don't have an option that says 13.4? Because I'm going to round 0.505 down to 0.5. That's smaller than 0.505. Do you guys agree? 0.505 is larger, not by a lot, but by a little bit. So I'm going to round down to 0.5. I can't have 13.50. Why? 4 sig figs. For that same reason, I can't have 13.51, but there is another reason that 13.51 would be wrong anyways. If this had been the digit that controlled the rounding, if 0 was my uncertain digit, 5 rounds even. And 0 is even, 1 is odd. So this is wrong for 2 reasons. It has too many sig figs and it rounds the wrong way. 13.6, I'm not using the right number. Yeah, I'm not using 5 to round, I'm using 0. So 13.6 is using the wrong number to do the rounding. So here's what I would round it to if I were stopping there. So let's plug it in and see what we get. Do you guys want to read off like 5 digits? Okay, and it keeps going, right? Grams per milliliter. Now, I had this number with 5 digits and this number with 4 digits, and we know that multiplication and division, we round to the least number of significant figures, but actually this just wasn't rounded. This truly has 3 sig figs, so I'm rounding to 3 sig figs here as well. I'm not necessarily rounding to 1 decimal place. Why did I choose 1 decimal place earlier? Because this number had 1 decimal place. This example did not go the way I wanted because there's like 3 sig figs all the way throughout, but I want to make sure you guys are tracking. I did addition. I had 1 decimal place as my smallest, so I stuck here with 1 decimal place, and that meant 3 significant figures. Now, I divide these 2 numbers, I still have 3 significant figures. Here's my 3rd significant figure. What answer do I report for this calculation? Kaden, you want to give it a shot? No. Okay. Ryan? 0.655 units, grams per milliliter. 2 is equal to or less than 4, so I round down to the 5. I get rid of everything else that's there. All right, should we do another one? You guys feel okay? Elena? I'm sorry, can you say that again? It really wouldn't matter. It wouldn't matter what I did here. It would, if these decimal places were the same, I still get this. What if I had taken a little bit of a better math? What if I knew that it was 1.005 plus 12.50 divided by this 20.61? Well, would you agree my answer now is this? Oh, Yeah, you're right. I also agree it's not that. I made a mistake. I added a 0 here, but that doesn't change what actually comes after my third decimal place. So it would be this. Thank you. Good catch. Not the mistake I meant to make. But instead of limiting myself to 5, my last significant figure is now 0. So how many sig figs in this final calculation? 4. Okay, let's extend this further. I've got 3 decimal places on both of my numbers, which means I actually still get that exact same number without rounding. Where is my last significant figure? Here. 3 decimal places. I did addition or subtraction, so I'm determining my number of significant figures by the least number of decimal places. These had the same number of decimal places, so I get all the way out to 3 decimal places for both of them. That means that my final answer gets to have how many sig figs? 5 sig figs. I know some of you are sitting there thinking, I don't know how to figure out what happens next to it or after this. And what I'm telling you is your first operation determines the number of significant figures. Now I'm going to do division by a number with less significant figures, correct? I'm going to divide 5 sig figs by 4 sig figs. How many digits should I get at the end? 5 sig figs. And this is where we can actually keep this longer answer, 0.65526 grams per milliliter. Actually, we should look back at it. This had a 4 afterwards, but 1, 2, 3, 4, 5 is my last sig fig, which means the 4 will get rounded. Okay, here is an example where I can divide 5 sig figs by 4 sig figs, and I'm not limited by the least number of significant figures. I'm limited by the least number of decimal places as determined by my first calculation. Does that seem fair? Okay. Good. Seems fair to me too. Actually, it doesn't. It feels weird, but that's the rule. All right, so let's apply it to some photon calculations, and then we'll come back to the molarity. Remember that you guys will be handed an equations sheet. You don't have to bring that equations sheet. There's nothing wrong with bringing it, but they might just tell you to leave it in the locker. I'm going to write up the equation as it's written on your midterm equations sheet. Should we pick some numbers, though? We're doing this was your question, right, Keon? We're doing the energy of light, the energy of photon, but we can also do, I guess I should have clarified. Do you want to look at the energy of light that is absorbed when an electron goes up in an energy shell, the energy of light emitted when an electron falls, and or do you want to do calculations from energy to wavelength, from energy to frequency? Okay. Okay, so we've got 2. What energy is emitted? Notice that light is actually not necessarily named, but we could have said, what energy does the photon have? What energy is emitted when an electron falls from shell 5 to shell 1? And then a second question, what frequency of light is needed to excite an electron from 3 to 4? It is important to recognize on your sheet that in order to do this second one, we actually need 2 different equations. This is just one equation, but to get the energy and then change that energy into frequency, we need a second equation. Do you guys know what equation I would use for this? I wish I had handouts of your equations sheet. Oh, and some of you probably can't even pull it up. Dang, Canvas being down is really bumming me out. I'm gonna wait for this to turn on so that you guys can keep copying this if you need to. But otherwise, I'll pull this down and I'll ask you guys, which equation should I use? Gabriel. Good. Change in energy. All right. Delta E equals negative 2.18 times 10 to the negative 18th joules times 1 over something minus 1 over something, and those will be the squares. I'm not going to fill them in yet because I want to put in the numbers. Keon, do you remember? This says N1 squared and 2 squared. What do I encourage you guys to think of N1 and N2 as? So initial minus final? Yep, it's the opposite. Final minus initial. How can we make that make sense? To do final minus initial. No, I agree. But unless you want the first thing you do to take this sheet and put NF minus NI, how else can we remember it? I remember it as like if I'm timing somebody, I'm going to take the time on my watch at the end and subtract the time on my watch at the start, final minus initial, and I'll get the difference between the two. The other way that you can do this, and this kind of sucks, we know that this delta E should have a specific value. Will this value be positive or negative for our equation? Should be positive. No, excuse me. Should not be positive. We'll think about it again. Light is going away, so the electron is falling in energy, should be decreasing. So I do want to get a negative number, which means if I plug all of this in and I get a negative times the negative, I did it wrong. So I'd have to flip them. So that's another way we can check that we're adding our numbers incorrectly. All right, what's my final state? My final shell? I'm dropping down to the 1 shell. So 1 over 1 squared minus 1 over 5 squared. By the way, how many sig figs here? What number limits my sig figs? No sig figs. Because, or excuse me, no sig figs in here because these are counted whole numbers. Whereas this has sig figs. So at the moment, 3 sig figs. All right, let's plug this in. I've got 1/2, no, excuse me, 1, because 1 squared is 1, minus 1 over 25. 1 minus 1 over 25. 1 over 25 is giving me a decimal 0.04. Does that have one sig fig? No, I'm doing a calculation on a counted number, 5, which means I get infinite sig figs there. 1 over 25 is a counted number as well. 0.04 is basically a counted number there. Seems odd, right? But 0.04, we're not going to limit to one sig fig. I've got infinite sig figs because it came from counted numbers. All right. 1 minus 0.04, I get a positive number here, 0.96. Which means multiplied by this negative value, I will get a change in energy that is negative, which means my electron has dropped in energy. Its energy, it has given off energy. Its change in energy is negative. So we plugged them in correctly, final minus initial. .96 times negative 2.18 times 10 to the negative 34. Thank you. I'm thinking of Planck's constant. You guys want to give me the answer rounded to significant figures? You want to give it a shot? Good. Oh, unit? Joules, great. Did anybody get something different? Carly, did you have to round up to the 9 from 8, or did you have to round down to the 9 from 9 something something something?
Yeah, down to 9 to 8.
Good. You had 9, 2 rounds down to just the 9. Anybody get something different? And why did you pick 3 sig figs over 2? Trick question. Good, exactly. The subtraction that we did here was with whole numbers, which means that is not really an operation that's limiting our sig figs. Or if it is, we're getting infinite sig figs, but that's not really what we're trying to say. We're saying that calculation with whole numbers is not limiting. So then we wait for the multiplication. That's our first true operation with significant figures. And since this is a counted number, essentially, I am left with 3 sig figs from here. I want you guys to notice something that's interesting. As you go to higher and higher and higher and higher energy shells, the difference in energy stays very close. That's because those higher and higher energy shells for the electron are very close together. Energy shell 1 and 2 are the furthest apart. 2 and 3 are much closer. 3 and 4, 4 and 5, 5 and 6. Until you get to a point where it'd be hard to determine with just 3 sig figs which energy shell you were actually falling from. All right, second one. What frequency of light is needed to excite an electron from 3 to 4? If I'm looking at my equations sheet, which equation will help me calculate the frequency of light? We know that we've got this change in energy that we're able to calculate. Is lambda what I really want? No, lambda is the wavelength. I want the frequency. So if I do solve for this, then I have to plug it back in up here and rearrange for frequency. I could also rearrange this right now. Frequency or lambda equals c over nu, and I could just plug in c over nu. If I've got c on both sides, then I could just divide by c, get it out of there. But then I've got 1 over nu. We're going to have to do probably 3 calculations here. So first of all, I want to find the frequency. Well, frequency is here, and frequency is here. That's pretty much all I've got. It doesn't have anything to do with the shells. That's where I have to recognize if I need to calculate the difference between the shells, I'll need a calculation like this. That calculation plugs in very nicely down here. And then I'll have to just do another calculation to solve for frequency. Do you guys want a chance to plug it in, or do you want to just watch me do it? Huh? Yeah. See if you can't plug in for those three equations and find the frequency of the light. Feel free to collaborate, work with each other, or raise your hand if you want some direction. Yeah. What do you mean? Oh, the other equation that was up there. Oh, yeah, sorry. Yes, it's exactly that. Yep. Mine is a little. You know, And don't forget your units. You got any units on that? You might have to guess. Oh, you guys have very different answers. How far did you guys get? Calculated the difference in energy. No? So we gotta use this equation first. You just took it, you plugged it in down here. It's not gonna bad. It's just gonna take up more space and be a little bit more challenging to kind of think about. I would actually just put delta E here and just solve for this. And as always, if you're getting confusion about how those numbers look in your calculator, just write them out in between each step.
So, after you do, I guess I didn't write the energy equation. So after you do the energy equation, and then you plug it into this one right here, do you just do this one?
Yes.
So you just divide by lambda, so we see over lambda equals your frequency.
Correct. Yep. All right, I want to point one thing out. I've noticed that a couple of you have taken this equation and you've started plugging in delta E here. There's nothing wrong with that. It's just going to get cluttered because we know that doing the delta E equation kind of takes a little bit of work. Sometimes it's nice to just spell it out once and plug it into your calculator. Other times it's nice to actually do it step by step and record the numbers you get in between so that you can feel confident in your calculations. So I would actually recommend not jumping straight into this equation, but starting with delta E equals and getting a number that corresponds to the energy of your photon. What is my final energy shell here? 4. And my initial? And a quarter squared, not even a quarter squared, 1 over 4 squared minus 1 over 3 squared should actually be a negative number. 1 over 3 squared is larger than 1 over 4 squared. If that's a negative number multiplied by a negative number, then my change in energy is positive. That's because my electron is being excited. And the nice thing is the positive numbers will transfer over into our next calculation nicely. But even with a negative number, when you're trying to get to the energy of a photon, just ignore the negative sign. A photon doesn't have a negative wavelength or a negative frequency. Once you solve for that delta E, then it plugs into the other equation much more nicely. Do you think you plugged it in differently this time?
No.
Okay. But the unit should not be joules. Yep. Do you know the unit of C? Yeah. Divided by the units of lambda. Meters per second divided by meters. Not seconds, but per second. Hertz actually is per second. Yep. Hertz is the unit per second. And now I think that you guys have the same number. Looks good. Did any of you plug in 1/16 minus 1/9 and get a number? Or did you just plug that in with the calculation times negative 2.18 times 10 to the negative 18? Yeah, you just plugged it right in. Because I want to point out, if you do 1/16 minus 1/9, you get negative 0.04861, and it looks like the ones repeat forever. So where do I cut it? How many sig figs do I get? Well, that's actually a fraction. Because again, it came from a counted number, so we could have done this. We could have gotten 16 and 9 to their lowest common multiple and taken the subtraction between them and actually just had a fraction number. And then multiplied by it. So I'm not going to limit sig figs anywhere there because it doesn't have sig figs. Tell me if this is the number you guys are getting for delta E. Positive, because I didn't multiply by the negative. Positive 1.0597 times 10 to the negative 19 units, joules. You guys got that? Okay. That's equation 1. Calculate the energy difference between the two. It is true, you could have just done that calculation on the bottom of calculation 2. But I guess I wouldn't recommend it. I would do it piecemeal. I would do this calculation first, get a number, and then continue. Although this calculation is going to limit my sig figs. I'm not going to round here as best I can, but how many sig figs will I be left with at the end of this whole process? 3 sig figs because of this constant that I was given. So if I were going to round now, I wouldn't put 1.0597, I'd put 1.06. All right, now I can calculate lambda. Lambda equals hc over this delta E. H is given to you. You don't have to guess it. 6.626 times 10 to the negative 34 joules seconds times 2.998 times 10 to the 8 meters per second. Divided by this 1.0957 times 10 to the negative 19 joules. Guys, why am I, well, yeah. Thank you. Why am I wasting my time putting units in here? Yeah, well, those were all pretty vague, but thank you. To be accurate, it's important for your ending. Honestly, it's a self-check. That's what it is. What if you plugged in a number wrong? What if you picked the wrong equation? Your units are going to tell you if you have put something incorrectly into here. This calculation should give me lambda. Lambda is wavelength. Wavelength has units of length. So if I don't get meters or something like that, I've done something wrong. So let's check that my units cancel. Joules times seconds, joules divided by joules. Joules cancels. Great, because honestly, joules is actually 15 units in a trench coat. So I'd rather just cancel joules with joules than figure out what joules is made up of. Seconds times meters per second. Seconds cancels. You guys agree with that? Seconds times 1/seconds cancels. So I'm left with units of meters. This is good. Now remember, if you didn't want to do this, you could have taken this long route of saying frequency is c over lambda. No, I'm sorry. You could have taken this long route of saying lambda is c over frequency, and then you would have gotten c over frequency is equal to hc over delta E. And then you got to do all this crazy stuff. You got to multiply frequency, multiply degree, change in E, divide by C, divide by H. So you could have actually just plugged that equation in. The frequency is equal to the change in energy divided by Planck's constant. But the algebra to get there is strange. Yeah, it's just, if you're strong with algebra, great, that's a good one to do. Or if you want to put that one on your cheat sheet and say other light equations, other forms of light equations, that's another one that you could write. All right, so let's plug in this number. How do you think I should round my sig figs here? Four sig figs? Or maybe I just don't round my sig figs here. That was kind of a trick question. I didn't mean for it to be. My calculator is giving me this. Lambda equals negative. How can it be negative? Oh, I plugged in a negative up there. It's not negative, sorry. I didn't multiply by negative over here, so I got a negative here. 0.000001875 meters. I don't like when my calculator does that to me, but I do want to remind you guys about exponents. If I've got 5 zeros in front of my number, that means I need to move my decimal place past all 5 of those zeros and then one more. So I can just convert this to say lambda is 1.875 times 10 to the negative 6 meters. Okay, that was my second equation. Now I've got the equation. I'll just spell it out. C is equal to lambda nu. I want to get nu by itself, so I'm going to divide by lambda on both sides. I'm also going to reorient this, so I've got lambda equals, nu equals C over lambda. And this is, again, I'm using the speed of light twice in 2 different calculations, which means there is a way I could have done this that doesn't involve the speed of light. Nu equals 2.998 times 10 to the 8 meters per second divided by this answer up here, 1.875 times 10 to the negative 6 meters. Think about those units for a second. How are they going to cancel? Anything to cancel seconds? Anything to cancel meters? Is it possible those meters actually double up and they become meters squared? Meters per second over meters. Meters over meters. Meters cancels. Am I left with seconds as my final answer? As my final unit? Per seconds is my final answer. And this is your friendly reminder that per seconds is called hertz. That's just the unit that we give to it. Is this number going to be very, very large or very, very small? Small? Big? 10 to the 8th divided by 10 to the negative 6th. With exponents, division can be treated like subtraction. So that's 10 to the 8th minus 10 to the negative 6, or really 8 minus negative 6, which is 8 plus 6. So I should get something on the realm of 10 to the 14th. We plug it in. Again, how many sig figs should I round this calculation to? This one I should round to 3. That one was not a trick question. All right, I'm going to show you what my calculator says. Remind me again, what's my unit? Hertz or per seconds. What should I round this number to? 1.5989333333 times 10 to the 14th. 1.599. Should I get 1.59, 1.60, 1.598, or 1.599? I'll scratch it. How many sig figs again? 3 sig figs. So what number is doing the rounding? 8 is going to do the rounding on 9. 9 rounds up to 0, or 10, I guess, right? Which means I'm not even going to have 5 in the answer. 1.6. 1.60, excuse me, because that O is significant, times 10 to the 14th hertz. There we go. What do you think? Is this a powerful wave of light that's needed, or is this a not very powerful? Pretty powerful? You're thinking about the hertz that it has? Let's think about this wavelength in a different unit. Instead of meters, what might be a nice unit for it? If I wanted to change 1.8 times 10 to the negative 6 meters into a different unit, should I go to kilometers? Nanometers would be small. Micrometers would be nice. This would translate to 1.875 micrometers, because I've got that times 10 to the negative 6. So millimeters would be something like, or sorry, nanometers would be something like 0.00187 nanometers. Millimeters would be a bit large, 187 millimeters, but not impossible. So actually fairly powerful, but not super powerful. This is not like ultraviolet light, but it's definitely not your microwave radiation. So it's in the range of, it's not radio waves, but it's not X-rays. It's actually in the microwaves, but microwaves are actually a bit longer than microwaves. Like, microwaves are usually in the hundreds of micrometers. Anyways. All right. How do we feel on these calculations? One of the most challenging parts is not just plugging it in, it's knowing what to plug it into and how many different equations to plug it into. I think if I can give you any piece of advice, it would be, do not let yourself get troubled if you plug into an equation and you realize it's not the right equation. Do you guys know how long you have on the midterm exam? You have 2 hours on the unit tests, correct? You have 3 hours on the midterm exam. Like 3 hours is a really long time to test. That is exhausting. But you've got the time to make mistakes and recover from it. So if it's a calculation that you're struggling with and you're just plugging it into the wrong things, take your time, take a breath. Plug it into as many calculations as you can, into as many equations as you can, until you find the one that actually gives you units that you can use, gives you an answer that you can use. Okay, the other thing we wanted to plug in here was molarity calculations. Usually these molarity conversions are a lot of multiplication and division. So in terms of sig figs, you're often just looking at the least number of significant figures. This is a good reminder. I might not take a break today. So if you guys want to move around, take a break, get some water, you're welcome to. But otherwise, I think that I'll just keep putting problems up on the board for us to look at. Whose question was molarity, by the way, Carly? Did you want to do dilution equations, getting the mass out of molarity, getting the number of moles out of molarity? Anything in specific?
Probably dilution.
Yeah? All right. I see I've got this dilution problem right here, so I think I want us to solve this. Oh, I made a mistake, but I can correct for it. What concentration is acquired when 10.00 liters of 2.00 molar, what is that? What is that, NH4OH? Sorry, I jumped to nomenclature early. Is that ionic, covalent, or an acid? It is technically, no, it's not an acid. It's ionic. It's ionic because I want you to recognize two common polyatomic ions that are present. NH4 and OH. Well, those technically aren't ions, right? Unless I say a charge with it, it's not an ion. NH4, what charge? If you're unsure, OH, what charge? OH minus, OH negative 1, which means NH4 plus, positive 1. You know the name of OH minus? What? Hydroxide. Hydrogen oxide, hydroxide. NH4 plus? Ammonium. You remember that ions often end with that -ium? Cations often end with that -ium part of their name. Ammonia is a very common chemical. Like ammonia is things that you want your plants to have so they can grow nice and tall. Ammonium is the cation version of that. Ammonia becomes ammonium. So if I have 10.00 liters of 2.00 molar ammonium hydroxide is diluted to 40.00 liters, what's our concentration? Remember, one of my tips here is that once you identify an equation that you can use, you can kind of list out all of the different variables with their values to kind of pull it out of the word problem. Is it obvious that this is a dilution equation? And is there a dilution equation given to you on your equations sheet? There is, and I want you to pay attention to how it's written. it's written on your equation as M1V1 equals M2V2. That's great if you're working with molarity. If you're not working with molarity, it works all the same. But M there really stands for molarity, when it could be C1V1 equals C2V2, and then be any concentration you want it to be. So what do you think we should call M1, V1, M2, and V2? Does it really matter what we call which variable? No. So long as we stay consistent that the initial volume and concentration are together and that the final volume and concentration are together. Anybody want to list these out for me? What would you put? People feel different ways about leaving this unknown. Some people just want to leave it blank. Some people want to put X there to say that's my variable, I'm going to solve for it. I like to put a question mark because I'm actually not going to substitute it for X. I just want to recognize this is what I'm aiming for. I'm going to leave it as M2 and I'm going to get an answer that solves for M2. Since I want to solve for M2, I want my equation on top to get M2 by itself. That means that I need to divide by V2. Remember, V2 divided by V2, that cancels out. I'm going to rearrange this. You don't have to, but I'm going to rearrange it so that M2 is on the left. M2 equals M1V1, over V2. I like to do all of that work before I plug in the numbers, just because plugging in the numbers has a lot more going on. And then doing the algebra to rearrange it has a lot more going on when I've got all of those measurements in there. But these variables are nice and compact, easy to move around. Now I'm going to start plugging them in. M2 equals 2.00 molar times 10.00 liters divided by 40.00 liters. All right, before we solve this, do we expect M2 is going to be greater than, equal to, or less than 2.0 molar? Good. I'm actually taking a specific number of moles, and I'm just spreading them out into a larger solution. So this should be a smaller concentration. Okay, why don't you guys plug it in? Tell me what you get. 0.5. 0.5 molar, closer. 0.50 and another 0. Why? 3 sig figs. I actually got more precision on my new concentration. Yeah, I got all the way down to the 3rd decimal place because I got to keep all 3 significant figures. You guys might have noticed if you watched my video doing the practice worksheet, there are some times where sig figs aren't really important, and a lot of scientists will just kind of arbitrarily round to 3 sig figs. It's just a good way of keeping a certain amount of digits without going too far and writing too much. But here we had 4, 3, and 4, so I get to keep 3 sig figs, my final answer. Should we take it a different direction this time? Do you want to set up something different than a concentration or a dilution? Or was that the example you needed to see?
Yeah, I don't think it was. I think it was something else, but I don't know.
So tell me if this sounds right. What if I wanted you to tell me how many grams of sulfite are in 5 milliliters of a 1 molar iron 3 sulfite solution? Yeah? Okay. Oops. That roadmap that I gave you guys in last week's worksheet, I know that it felt confusing to a number of you. So I want to point out kind of how I can create the roadmap that I want to here, just using this. I have information in molarity, and I'm going to use the volume, specifically molarity of something, A, which is this iron. Oh, I put iron 2 sulfite. And that's okay, but I think I said out loud iron 3. What do you guys want to do, iron 2 or iron 3? Iron 2 is awesome. If I have concentration of A, iron 2 sulfite, then I can use the volume to get to the number of moles of A. And from moles, I can go to particles or to mass or to moles of something else. Do I want to go to mass of iron 2 sulfite, or do I want to go to something else? If I go to mass now, I'm not going to get mass of sulfite. I'm going to get the mass of iron 2 sulfite. So just to be clear, I could use the molar mass of A, and I could get grams of A. But that's not what I'm looking for.
You go to like from iron sulfate to sulfate.
That's right. Sulfite.
Sulfite.
Sulfite to sulfite. Yep. I'm going to need to do the mole to mole conversion, which means I need to know the chemical formula. Well, I would have needed the chemical formula to get the molar mass anyways. Once I get to moles of B, then I can use the molar mass of B to get to the grams of B. And remember, if you build something like this on your cheat sheet, similar to the thing that I gave you on the worksheets last week, then all you have to do is just land yourself somewhere and say, this is where I am, this is what I have information about, these are the conversions I'm allowed to do, these are the places I'm allowed to go. And this is what we want to do right now. We want to go from concentration of iron 2 sulfite to grams of sulfite. Do you guys want to take 5 minutes and try setting it up on your own? A multi-step conversion. That's all it is a multi-step conversion. Feel free to do it in portions or do it completely in sequence at once. I'm going to come around. If you are not even sure what to start with, tell me. Oh, you know what? I wanted to say it differently. Something felt wrong about the roadmap I gave you. Here, I'm going to point it out. Molarity versus volume. Which one is a conversion factor? What does a conversion factor need? 2 units. Like 1 meter is 1,000 millimeters. That's a conversion factor, and it has 2 units. Or 1 gram per 1 milliliter, density is a conversion factor. 1 gram per 1 milliliter, 2 units. What is a conversion factor, molarity or volume? Which one has 2 units? Molarity has 2 units. Moles per liter. So on that roadmap, I shouldn't have put molarity with volume as the conversion factor. All of your conversion factors have 2 units, but I made that mistake on that worksheet. This should have been the volume of A, where molarity, moles per liter, is what allows you to convert between volume and moles. Given that information, the way that you start setting this up actually changes a little bit. For instance, you're not landing with information you know about molarity anymore. You're landing with information you know about volume. And once you know information about volume, you can use molarity as a conversion factor. So you're going to start by having a calculation that has volume, and then try to get the units of volume to cancel out so that you get into units of moles. You live in your line. Ashley?
Where is that on the sheet?
It's on the worksheet I gave last week. Notice how the groups coming up and down from your roadmap at the top, they say molarity, and they have volume as the conversion factor. And that's the mistake. I should have had volume at the top. Molarity is a conversion factor. Okay, I'm going to give you guys one more hint about this problem. If molarity is a conversion factor and its units are moles per liter, what do I need to do with my initial volume? Convert it into liters. You can just plug that into your multi-step conversion. You can just plug in the milliliters to liters conversion, and then liters to moles, moles to moles, moles to grams. All right, hang on. Let's just keep going together. We got to figure out the chemical formula of iron 2 sulfate. We have to know it. Is this ionic or covalent? One more time. Ionic. How do you know that? Metal and a non-metal. Yeah. Well, actually, a metal and a polyatomic ion. Sulfite is one of the polyatomic ions we have to know. But the fact that iron is there tells us it's ionic. Okay, what's the charge on my ionic iron? How do you know it's 2? Got that parentheses 2. That's what nomenclature is telling us. Is it 2 plus or 2 minus? One more time. Yeah. Cation always comes first. So iron 2 sulfite. Iron 2 is the cation. Sulfite is the anion. Sulfate is a very common ion. Sulfite has a different number of oxygens, but the same charge. Do you guys remember sulfate or sulfite? Which? All right, I'm going to give you some. No, I'm hearing SO3 and SO4. Okay, but I'm also not getting a charge. Good. Sulfate and sulfite are both 2 minus ions. Which one has fewer oxygen, 8 or ite? Ite has fewer oxygens. So sulfate is the very common SO4 2 minus. Sulfite has 1 less oxygen, SO3 2 minus. Great. Box method or crisscross, which one would you guys like to use to solve for the chemical formula? Do you need it? Keon, what do you think? How could we try to do this? If we used the crisscross, would we get Fe2, SO3, 2? No, something feels off about it? What? They've got the same number. If we're using the box method, this can actually help demonstrate that a little bit better. How many do I need of each to balance each other? I need one. I need one Fe2 plus. I need one SO3 2 minus. That's what feels wrong about this. Why do I need 2 irons and 2 sulfites to balance each other if just 1 to 1? Remember, this was the crisscross method. We use charges to predict subscripts. And I want to say this again because I know it confuses a lot of students. The charges are not becoming subscripts. It's just a shortcut. It's a way to predict the subscripts that we would need. But if those are the same, or if they have some common denominator, we divide by that common denominator to get the lowest ratio of ions necessary. And here we can see it's just 1 to 1, 2 divided by 2. So my chemical formula is FeSO3. Okay. By the way, how many of you think you're taking up space on your cheat sheet with ions? Yeah, good idea. The ones you know, don't put them on there. Don't waste the time or the space. But the ones that you always forget, the ones you struggle with, put those on there. No, I think you can write in color. Yeah, it just has to be handwritten. So if it's markers or colored pencils or crayons, it should be fine. Yeah. I have another question about this. Is this a chemical formula or empirical formula of iron 2 sulfite? Can it be both? It can be both. So it is both. It is both the lowest ratio of the ions present, and it is the smallest repeating unit within that crystal structure. So it's both empirical and ionic. All right. Now do you want a few minutes to try setting it up? Or should we go through it together? Okay. What information do I know? I know volume. I have volume here. So I'm going to start with the information that I know. 5.00 milliliters of iron sulfate. If you want to abbreviate, instead of putting like FeSO3, you can find ways to abbreviate, but I cannot encourage you enough to be as detailed as possible, be as specific as possible. We mentioned earlier that I can't put molarity yet. I can't put moles per liter because liters doesn't cancel. You might not catch that on the exam. You might just set it all the way up and then start realizing liters and milliliters doesn't cancel. That's an easy fix. Just do a simple conversion from milliliters to liters. Remember, I recommend putting in all of your units. We'll come back in and put numbers later. Now that I've got liters of iron sulfate, I'm going to cancel liters of iron 2 sulfate using molarity. Moles per liters. That's a conversion factor. That's my molarity. I'm going to come back to put numbers in. I'm setting up all of my dimensional analysis right now. I don't want moles of iron sulfite. I want moles sulfite. SO3 2 minus. But I don't want moles of iron sulfite, or I don't want moles of sulfite. I want mass. I'm gonna need molar mass, but I want mass of iron sulfide.